Okay, guys. In the last video, we thought about this car moving, and we had said that we could talk about its motion in terms of this equation, that the position x at any time t would be given as this expression 2 minus 4t plus 2t squared, and then we looked at a table of values giving the position as a function of time, and then we talked about displacement and then average velocity over a variety of time intervals. Well, one thing I sort of hinted at is it might be interesting to know what its instantaneous velocity at any moment of time would be, and that's what I'd like to talk about right now. Before I do, it might be helpful to take a look at a graph, like what would happen if I graphed x as a function of t. In other words, if I graphed this, and I've done that for you. I've got a graph here, and this graph gives the position as a function of time. So position increasing values of x are here, and increasing values of t are here. And you can see what I've done here. I've graphed the first 3 seconds, and exactly what we had noted is evidenced here. This is t equals 0, right? Where is it? Well, it's at positive 2. T equals 1, it's at 0. T equals 2, it's back at positive 2. And then t equals 3, it's up here at 8. So we can see these values right here. We can see those values on this curve. But we do note that there's a curve here. There's some curvature, which is interesting. We can talk about what that curvature means. So here the position of the particle is given by this graph. I want to point out, I think you know this, but don't think that this curve means that the car is moving in 2 dimensions. It's moving back and forth along an x-axis, right? So, for instance, its displacement in the first second would be represented here. It would be from here to there. That would be the delta x in the first second. In the second second, it would be from 0 back up to 2. Right? We could think about what would the displacement be for the entire interval, 0 to 3 seconds. Well, for that entire interval, the displacement would be this. Right? This would be the beginning. This is x0, and this is what we would call the final position, which is x at 3 seconds. So that would be the entire displacement for the 3-second interval from here to here in a straight line. All right, well, that's something about position, something about displacement. What about these average velocity values, right? How do we represent the average velocity values? So if I wanted to know the average velocity, let's take a look at this line right here. If I wanted to know the average velocity for the entire interval, 0 to 3 seconds, graphically, what is the meaning of that? Well, that would mean, if we remember the average velocity, I'll just write it over here, the average velocity is the change in x, so x minus x naught, over the change in time, t minus t naught. In that case, we'd be thinking about x at time 3 minus x at time 0 divided by t minus t naught, which is, of course, 3 minus 0. Well, what is the meaning of this expression in the graph? Hopefully you can recognize that is the slope of a line, and it's the slope of the line connecting these 2 points. I'm going to try to draw that. We call this a secant line. See if I can draw this relatively straight. It's not too bad. So this is a secant line. And this, the average velocity, the slope of the secant. So slope of the secant gives us the average velocity in this case, right? So the slope of this line would be what? It would be, in this case, positive 2. In fact, I think we can see that, right? We can see that if we take a look at these 2 points, right, from here to here, it goes from 2 to 4 plus 2 in 1 second. So indeed, the slope is positive 2. Fill in that gap right there. Okay, well, now let's think about instantaneous velocity. Well, first of all, what's an instant? What is the meaning of instant? Well, instant means a mathematical moment, or delta t equals 0, right? We're imagining that this is shrinking to 0, which of course represents a problem algebraically. You can't divide by 0. So how do we think about this delta t as being 0? Well, there's a way of doing that, which is the derivative, right? We can think of this rather than delta x over delta t, we can think of dx over dt. In other words, the derivative with respect to time of the position function. And remember, the meaning of these little d's in some sense is an infinitesimally tiny delta, right? A delta that's down to 0. So this would be an infinitesimally tiny delta t and an infinitesimally tiny delta x. And one way to think about that, and you probably did this when you first talked about the derivative in calculus, we could think about that by taking these two positions and kind of shrinking the delta t down to some very small value. So for instance, if I wanted to know, let's say I want to know the time right there. That's not showing up very well. Let's take a different color. What if I want to know the time right there at that instant? Okay. Well, one way you could try to do it is to just take a really small delta t. So maybe I take my delta t from there to there, right? So I could take this itsy bitsy teeny delta t. So in other words, this right here is my delta t. Small delta t. And then I could take a look, this is going to be tricky, at these corresponding points in terms of the position. And so now this right here, that is my delta x. And I could say delta x over delta t, and then what would I be finding? I'd be finding the slope of the secant line connecting these 2 points, which maybe is a pretty good approximation of the velocity at that instant right here. But of course, it's not the same thing. So what I have to do is to imagine shrinking this delta t to 0. And what happens to this secant line, this delta t becomes 0? Well, it's no longer a secant line. It becomes, of course, a tangent line. So the slope at this point, the slope of the line tangent, in terms of the graph, that's really not a good tangent line. The slope of this tangent line is going to give us the instantaneous velocity. So this v, and note I'm not putting a bar over here because dx dt, this is the instantaneous velocity. This is equal to the slope of the tangent in terms of the graph. And then in calculus class, you no doubt did this, did a bit of work with limits to try to figure out, well, what is the meaning of that, with the slope of the tangent line, and we now know it's pretty straightforward to take this expression and figure out what would be the slope of that graph at any given point in time. We know how to take the derivative of that. So this velocity, if we wanted to give the velocity as a function of time, we could say that the instantaneous velocity at any time is the derivative of this thing, which is going to be -4 plus 4t. So -4 plus 4t. And that now, this is now an expression that will allow us to find the velocity at any instant t. So you can plug in any value of t here, and it's going to allow you to figure out the velocity at that instant. So, for instance, I picked a point that was at 2.5 seconds. So if you plugged in 2.5 here, you would then figure out exactly what the velocity is at that moment, and we could do that. So 2.5 times 4, that's 10, minus 4 is 6. So at this point, the slope of this tangent line would be +6. So we know at that instant of time, at 2.5 seconds, we know that the velocity at that instant is 6 meters per second. An instant before, it's going a little bit slower. It has a slightly less positive velocity. An instant later, it'll be slightly greater. But at that instant, according to this expression, it's exactly equal to 6. So, using the derivative, we can go ahead and figure out, if we know the position as a function of time, we can figure out the velocity as a function of time. And what I've done now is I've gone ahead and graphed this thing. So the next bit is the graph of this function. So this is, I'll put it down here, this is the velocity as a function of time, which we said is -4 plus 4t. So here is graph of this. It's a linear function. Might be worth taking a look at this and figuring out what the meaning of some of these points are. What is this? Okay, what is this? This is t equals 0. What is t equals 0? Well, that's our initial velocity. So our v naught is this point. V naught, if we plug in 0 here, this term vanishes, and v naught is -4. The initial velocity is -4, so this is v naught, which makes sense that it's negative. We noted in the car that the initial movement is negative, right? It moves initially in the negative direction. Okay, so the initial velocity is -4. How about this point? What is this? This is at t equals 1. What's going on there? Well, at this point, the velocity is 0. So at v equals 1, the velocity is 0. What does that mean? That means that it's changing directions. It is stopped, and in terms of this car, it's changing directions, right? It's gotten over here, it's moved in the negative direction, now it stops for an instant of time, and then begins moving in the positive direction. Okay, so that's what's going on here. It has moved in the negative direction, and what's happened? It has slowed down. Now, I want to point out the velocity is increasing here, right? But the speed is slowing down. The velocity is increasing in the sense that it's becoming less negative, but the speed is decreasing in the sense that the car is going from moving to stopped. And then as we cross over the t-axis, yeah, maybe I should note that these are values of t, right? Increasing values of t, and these are values of v here. So as we cross over the t-axis now, the car is now moving in the positive direction, and its velocity is increasing and its speed is increasing as we move to positive values of velocity increasing. And then here we have the velocity right here at 3 seconds, which happens to be, in this case, 8 meters per second. We noted before, we found up here, we said what was the velocity at this moment? 2.5 seconds. We plugged in 2.5 and found positive 6, and you can see that here. Here's 2.5 seconds, and indeed positive 6 meters per second at that instant of time. Okay. A fair question you might ask is, okay, well, what does the slope of this line mean? I'm not going to answer that right now. That's going to be our next video. So hold off on that thought. We'll get back to that next video. For now, what I want you to get out of this video, first of all, is if you have an expression that gives position as a function of time, you take the derivative with respect to time, and you get an expression for velocity with respect to time. And then this little exercise gives us the graphical meaning of that relationship. That's all for now.